Continuing with our parallel plate capacitor, we're going to try and show the application. And so I'm going to switch things around a little bit. Last time I had the positive plate on the top and the negative on the bottom. And I'm just going to switch around. How would the electric field look for this setup? Well, it's going to go like this. The electric field points towards the negative charge. However, I think it's very, very easy to forget what these arrows mean. And even often I'll say, well, that's the direction things will move between these plates. And what's more important is that it's the direction that a positively charged object, a positively charged thing, would move in between these plates. Versus, well, what if we had the exact same plate setup, however, draw that a little bit better. However, what if we said, well, what would happen? How would a negatively charged object behave in this setup? We have to think that's how a positively charged object would behave. A negatively charged object is going to want to move towards a positive plate. And that's very important for our application of a parallel plate capacitor, or just a capacitor, in circuits. So this is a positively charged object. This would be a negatively charged object. So this is negative behavior, let's call it, versus the positive behavior. So let's draw a simple circuit here. We're going to have a battery. And that battery is going to connect to a resistor and an LED. So here's our LED, here is our resistor, and this is our voltage source. Okay, so let's build that circuit, which I have right here, and let's hook it up and see what happens. So there's our circuit. Our resistor is here, and our LED is there. And this is our voltage source right here. And just disconnected. What's important to note is that now we want to look at what happens when we connect a capacitor, which is going to look like that. And as we do that, you can think about what's actually happening in a circuit. And here's our negative end of the terminal. Here's our positive end terminal. And we're going to connect a capacitor parallel to our LED. So here is our capacitor. And we'll connect that in parallel. So let's just let's turn this off just to be safe. noticed how our LED turns off. So that's kind of the point of the capacitor. Once I connect this, we'll turn it back on again. And it turns out that the on function doesn't really change anything. But the point of the capacitor is, well, no electricity is allowed to flow through the capacitor. And so these electrons at the beginning are going to flow, and they're going to go through our resistor. When I connect a capacitor, they're going to go and they're going to start to build up negative charge on this end of the capacitor. Any negative charge that was here on this end is going to want to go back to the battery. It'll have a very strong pull of those electrons, and so all the electrons vacate this end, leaving it positively charged. And electrons that flow through the resistor and LED are going to go straight back to the battery. And so the voltage source here of the battery kind of leaves this state present for our capacitor. And so what happens when we disconnect the battery is we have our resistor and our LED, and the only thing that's still hooked up is our capacitor. And there's a lot of electrons here, and electrons want to be with positively charged protons. And so these electrons, beforehand, there used to be a lot of electrons flowing through here, and so they didn't really want to go this way. Now that's not there anymore, and so these electrons are going to flow around and back to the positive end. And so even after our battery, the thing supplying power to the LED, is gone, there will still be some electrons flowing into the LED. Until this capacitor runs out, that LED will stay lit, and we should see some different effect when we turn it off. And so instead of completely turning off quickly, it kind of fades away when we turn off the battery. You can say, well, I didn't really disconnect it. Well, I can easily just pull the battery away. And so that kind of reveals the importance of a capacitor, the application of a capacitor, being that LEDs and other electrical devices sometimes don't do well with sudden surges of electricity or sudden gaps in electrical power. So the capacitor is put in place to make sure that if the power increases or decreases suddenly, the capacitor can kind of weather that storm for the LED, so to speak. So that's kind of the application of some of the stuff we're looking at. What we want to look at now is, we'll call it EM number 7, because we're looking at something called electrical potential energy. And it behaves a lot like some of the energies that we looked at last semester, including gravitational potential energy, elastic potential energy. This is another type of potential energy. It's electrical potential energy. So the electrical potential energy has to do with the idea that it's going to take some energy to move electric charge. And so I want to start with a few of the things that we absolutely know. So things we know. Well, we know that the change in any potential energy is equal to the work. We also know that the work is equal to the force multiplied by the change in distance. So in terms of energy, in terms of all of this, it's going to take a force to move something a certain distance. In terms of gravity, gravity takes an object like this, and if I want to move it a certain distance upwards, let's say I want to move it 3 meters upwards, that's going to take and require some amount of force. And so this is the case for, we call that EPG. Yeah, gravitational potential energy. The same can be said of elastic potential energy and also of electrical potential energy, which we're going to denote electrical potential energy by just this. This is where notation starts to become a bit of a problem. This is our electrical potential energy, and this is our electric field. So, and they're going to sometimes often be used in the same equation. So important to note, arrow overhead, electrical field. No arrow, electrical potential. Sorry, electrical potential energy. Now, what we may also want to say is, okay, well, if the change in potential energy is equal to the work done, and the work is equal to the force multiplied by the displacement, is it okay to say that the electrical potential, or change in electrical potential, is equal to force multiplied by delta D? And the answer to that question is sometimes. But not always. Let's go with the examples that we kind of do know. For gravitational potential energy, this is almost always the case, because if I move an object 3 meters, it requires a certain amount of force. We'll call that just force 1. If I then take that same object and I move it upwards another 3 meters, well, the force that it takes to move another 3 meters is the exact same force it took to move this 3 meters. And if I moved it another 3 meters upwards, it would take the exact same amount of force, because the gravitational field is the same for each of those sets of 3 meters. This is where I can use this. An example last semester that we saw where we couldn't use that was elastic potential energy. I'll have you recall that that has to do with springs, and the more we stretched a spring, the more force it took to stretch it the same amount. It got more and more difficult to stretch that spring. So that's kind of where we've seen, yes, it works for some cases, but not all the time. And electrical potential energy is another one of those cases where, in fact, it sometimes can be this, but it also sometimes cannot be this. So let's go with the case where it cannot be this. Let's go with a negative charge and a positive charge. And let's say, just for simplicity's sake, that these two charges are 1 meter apart. And then I want to move this charge another meter away. Okay, so I want to make it go from 1 meter away to 2 meters away. I can't see that that's so. Now, this will do a few really fundamental things. And the first is, well, these two things are attracted to each other. So similar to the object that's attracted to the Earth, it's going to actually take force to do that. So this will require a force. So we'll call that force 1 as well. That's going to require force. It'll move at a distance. It will do work on that charge. And this will also change the energy of the system. But then if I take that charge and I move it another meter, if I take it from here and move it another meter, that will be the same distance, but it will be a force, a different force. We'll call it F2, just like we did here. Now, in gravity, F1, we said, was equal to F2. But that's not the case here. Because we have to remember that this force that we're trying to apply here is the thing to basically cancel out the electric force. So the electrostatic force. The electrostatic force is equal to kq1, q2 over r squared. The force depends upon how far away you are. So if you're further away, it's going to take less force to move the same distance as it did before. So that's the really important kind of fundamentals behind this equation here. And so what we find is that had to do with a little bit with the electric field, because the electric field, well, that has to do with the force. So for this particular charge here, the electric field is not uniform. And that's the key kind of thing that we were looking at the last video. And so where do we see something that the electric field is uniform? Well, that's in our parallel plates. So kind of separate this. So in our parallel plates, the electric field is uniform. Well, that means that the strength of the electric field is the same everywhere. Which means that the force is the same everywhere. Any charge that exists within this field will experience the same amount of force whether or not it's here or here. And therefore, if a charge moves from here to there, or from there to here, the same distances, it'll experience the same force to do that. Well, that's where we get to actually say that the change in electrical energy, electrical potential energy, is equal to the work done, and then that can also be set equal to force multiplied by displacement. And this equivalency is only for uniform electric fields. This whole thing here, only for uniform electric fields. The next thing we'd like to touch on is again, this is going to get a little bit strange, but I think highlighting everything is really important. So electrical potential energy is this here, this delta EP, representing the idea that, well, the energy of something actually changes when you change how far away it is from an object. Now that still happens here. I just can't use that full relationship. The energy still changes in both of these. So, for example, what that could look like is a positive charge starts out here. And being a positive charge, it wants to move to this location. It does so, and the energy changes. Now, if I kind of think about this, this looks a lot like a falling object. So the energy becomes less. And if there's less energy, well, where did it go? And so that leads into our conservation of energy, and the actual positive charge should pick up some kinetic energy, and that change in energy is equal to the work done, which in this case can be equal to force multiplied by displacement. And that change in energy, or gain in kinetic energy, for this gap here is the exact same for this here. This cannot be said here. In order to perhaps start to do calculations here, we actually need a different level of math. We'll leave that at that. However, what we can start to do, especially for this uniform electric field, is instead of describing, we have a whole different thing called electrical potential, electric potential. Electric potential is related but not the same as electrical potential energy. Electrical potential is electrical potential energy, but for one unit of charge. So electrical potential is the electrical potential energy, is this delta EP, but for one unit of charge. And actually isn't really a delta EP. It's actually just what is the energy at one location. Whereas this is what is the energy between kind of two places. This would just be saying what is the energy for that unit of charge at a location. This is the electrical potential. This has a different symbol called V, which stands for volts, and is represented by, well, this is energy, so that's joules. Charge is coulomb. So a volt is a joule per coulomb, and a volt can be represented by the energy that a particular charge has at a location.